Based on the architectural layout, the short span Lx is 3000 mm and the long span Ly is 3600 mm. Since Ly per Lx is 1.2, which is less than 2.0, this is a two-way slab. I am using concrete grade FCK25 and steel FYK 500. Based on Eurocode 2, Table 5.8 for fire R60, the minimum thickness is 80 mm. However, to satisfy deflection, I have estimate and try a thickness of 125 mm. For durability, fire and bond requirement, following Eurocode 2 Table 4.4n, I calculated a nominal cover C-norm of 25 mm. This accounts for durability in an XC1 environment and fire resistance. I calculated the total design action N using the formula 1.35 GK plus 1.5 QK. Including the slab self-weight of 3.13 kN m², the total design load is 10 kN m². Referring to BS 8110, Table 3.14, Case 4, I identified the bending moment coefficient for a panel with two adjacent edges discontinuous. This allowed me to find the design moment for both the short and long spans. For the main reinforcement, I begin the reinforcement design for the short span. Effective depth for the short span dx is 96 mm. Midspan and support, I calculate the K values for both the midspan. MSX1 is 4.23 kN per m and the support MSX2 is 5.67 kN per m. In both cases, K less than 0.167, meaning no compression steel is needed. After calculating the lever arm Z, which is kept at 0.995 D, the required steel area AS for the support is 142 mm² per m. I choose H8 300 for both top and bottom. Now for the main reinforcement also, but this time is long span. Follow the same process for the long span. Effective depth here dy is 88 mm because these bars sit on top of the short span bars. The midspan moment is 3.06 kN per m and the support moment is 4.05 kN per m. The required steel areas are 121 mm² per m and 160 mm² per m respectively. Again, I specify H8 300, which is 168 mm² per m, to maintain uniformity across the slab. I check the minimum reinforcement area AS min using Eurocode 2 9.2.1.1. The result is 134 mm² per m, which confirms my choice of 168 mm² per m is correct. The maximum shear force VED is 14.1 kN per m. Using Eurocode 2 6.2.2, I calculated the concrete shear capacity VRDC. I found the size effect factor K to be 2.0 capped from 2.4. Final VRDC is 38.04 kN, which is much greater than our 14.1 kN load. The slab is safe in shear. For deflection, this is a critical check. Using the long formula from Eurocode 2, section 7.4, I calculated the allowable span to depth ratio. The allowable ratio is 142.66, which our actual ratio is only 31.25. This slab is very stiff and will not have deflection issues. Now we go on cracking. Based on Eurocode 2 7.3.3 and 9.3.1, I checked the maximum bar spacing. For a 125 mm slab, the limit is 3075 mm. My choice of 300 mm spacing is well within the limit. For final summary, the detailing shows the layout of the H8 300 bars for both top and bottom reinforcement with a concrete cover of 25 mm. This completes the structural design of slab 1.
Assalamualaikum for Syed Muayyad. My name is Amir Lukman Hazik bin Sordin. I want to present about slab. This presentation details the structural design of two-way slab panel D2E and 525A, accordance with Eurocode 2 standard. Slab classification with a long span of 2500 mm and a short span of 1800 mm. This aspect ratio of 1.4 confirms the panel function as two-way slab. Initial sizing to safety deflection control requirement, we have select a trial slab thickness 80 mm. For the design specification and material, environmental constraint. Design account for 50 years service life with an XC1 Expo class and 60-minute fire resistant rating. Material strength. We utilize grade C25/30 concrete and the grade 500 high tensile steel to ensure structural integrity. For the cover requirement, to meet durability and fire safety standard, nominal cover of 25 mm applied to allow reinforcement. For the loading and structural analysis, load assessment. The design consider permanent action is 3.5 kilonewton per meter square and the variable action is 2.5 kilonewton per meter square. Design load. Applying the Eurocode partial safety section, the total ultimate design load is calculated as 1.35 plus 1.5 is equal 8.48 kilonewton per meter square. For the moment coefficient, using the coefficient for the 4H continuous panel, the critical design moment is found at the short span support is 1.37 kilonewton per meter. For the reinforcement design, effective depth for X is 52 mm and for the Y is 46 mm. Reinforcement selection, while the required steel area is relatively low, we have provided H6 300 reinforcement throughout the panel. Efficiency, the provided area of 94 mm square per m comfortably exceed the minimum reinforcement requirement for all span. For the shear and serviceability variation. Shear capacity. The concrete design shear resistance is 20.2 kN is significantly higher than actually designed shear force is 6.56 kN, confirming no shear reinforcement is required. Deflection control. The actually span to effective and the depth ratio of 24.6 is well within the allowable limit of 405, ensuring the slab remains stiff under service load. Cracking limit, spacing and tightness requirements are satisfied, ensuring the slab meets all serviceability limits set for the long-term performance.
Hi, my name is Raiti Binti Jeffrey. My number metric is 07 DKA23 up to 003. Today I will be present the structural design calculation for continuous beam, specifically beam C 1 to 4 as part of our reinforcement concrete design. This design process covers everything from determining the initial specification and loads to analyze the shear force and bending moments, and finally design the main and shear reinforcement while ensuring serviceability limits are met. Let's start with the basic specification. Beam C 1 to 4 is a continuous beam spanning across 3 equal bays, with each span being 5 and 0 meter. The beam dimensions are 200 mm by 550 mm, supporting a slab that is 100 mm thick. For the materials, we are using a characteristic concrete strength of 25 Newton mm and height yield steel with a strength of 500 Newton for both the main bars and the links. We assume a nominal concrete cover of 30 mm. First, we need to determine the action on the slab and how they transfer to our beam. Since the Ly divided Lx ratio is less than 2.0, the slab acts a two-way spanning slab. Using the a priori shear coefficient from table 3.515, we distribute the permanent and variable action from the slab to the beam, resulting in a total design load of 38.93 kN per m. Because the beam is cast monolithically with the slab, it acts as a flange section. Specifically, a T-beam, we calculate the effective flange width for the different spans to ensure we accurately capture the beam compressive capacity. Next, we move to the structural analysis. Since we are dealing with a continuous beam with equal spans and uniform loading, we use the standard moment and shear coefficient to plot our bending moment and shear force diagrams. As you can see, our maximum shear force F comes out to 154.65 kN. With the bending moment, we proceed to design the main longitudinal reinforcement. We analyze both the midspans and the support. For example, looking at the midspans, we calculate the effective depth and check the K value against K bar to verify that compression reinforcement is not required. We confirm that the neutral axis falls within the flange, which simples our lever arm set calculation based on the required mass of steel AS. We selected suitable height yard bars like the 1H20 bars provided, ensuring that the area provided strictly falls between the minimum and maximum allowable limits. Next, we tackle the shear reinforcement. We calculate the design shear force VED at the supports. Our first steps was to check the concrete strut capacity to ensure the section wouldn't fail by wet crushing. Once the concrete capacity was verified, we calculate the required shear links ASW divided S for the internal supports 2 and 3. Where the shear force are higher, we determine the required spacing for H6 links for the end supports 1 and 4. Where the shear force is slightly lower, we adjust the link spacing accordingly. Point to the link arrangement diagram. We also map out the link arrangement. Identify the zones where we can reduce the shear reinforcement to nominal medium links once the shear force drops below a certain threshold. Finally, we must ensure the beam performs well under everyday use, which means checking the serviceability limit stage, specifically deflection and cracking. For deflection, we calculate the allowable spans to effective depth ratio using the necessary modification factor for the structural system, flange width, and the amount of steel provided. Our axial ratio of 9.26 is well below the allowable limits of 28, so deflection is perfectly fine. For cracking, we'll calculate the stall stress under service loads and determine the maximum allowable bar spacing. Our axial bar spacing is 51.5 mm, which is well under the 150 mm limits, meaning crack widths will be safely controlled. In conclusion, all ultimate and serviceability limit state checks has been satisfied. The proposed beam size along with the calculated main and shear reinforcement provided a safe, efficient, and compliant design according to the required standards. Thank you.
Assalamualaikum dan selamat sejahtera. Nama saya Muhammad Iqmal Hanif bin Jumian, kad matrix 07 DKE 23F 1081. Saya akan membentangkan BIM 2. Untuk bahagian ini, rasuk C14 dianalisis menggunakan kaedah moment distribution dengan satu susunan beban di mana 3 case telah diambil kira. Case pertama, semua dikenakan beban yaitu 1.35 JK tambah 1.5 QK. Case kedua, span 1 dan 3 dikenakan beban maksimum, manakala span 2 beban adalah minimum. Rasuk ini mempunyai 3 span sepanjang 5 meter dan lebar tinggi 550 dan 200 mm. Nilai beban JK 17.84 dan beban QK ialah 9.9 kN. Seterusnya, momen inersia digunakan formula BH kosa 3 per 12 dan diperolehi nilai 2.77 kali 10 kosa 9 mm kosa 4. Kemudian faktor pengagihan ditentukan sekitar 0.43 dan 0.57. Bagi case pertama, semua span digunakan beban maksimum yaitu 1.35 JK tambah 1.5 QK bersamaan 38.93 kN per meter. Langkah pertama, kira fix end moment menggunakan formula WL kuasa 2 per 12. Hasil semua span mempunyai nilai moment sebanyak 81.1 kNm. Selepas itu, jalankan kaedah moment distribution menggunakan pengagihan vektor 0.43 dan 0.57. Proses ini melibatkan pengagihan moment dan carry over sehingga mencapai keseimbangan. Daripada jadwal, momen akhir diperoleh yaitu 103.8 kNm di join 2 dan 73 kNm di join 3. Selepas itu, kirakan daya Ricci menggunakan persamaan keseimbangan momen, dan ini adalah data yang saya telah perolehi. Seterusnya adalah case kedua. Langkah pertama, kira fix end moment menggunakan formula WL kuasa 2 per 12 dan nilai momen bagi setiap hujung span ialah 81.1 kNm dan pada span yang di tengah ialah 50.2 kNm. Seterusnya saya menggunakan kaedah moment distribution dengan vektor 0.43 dan 0.57 untuk mendapatkan momen akhir setiap sambungan. Selepas beberapa iterasi, momen akhir diperoleh sekitar 79.4 kNm di sambungan tengah. Dan yang terakhir, daya Ricci menggunakan persamaan keseimbangan. Nilai daya Ricci yang diperoleh berbeza bagi setiap span bergantung kepada beban yang dikenakan. Seterusnya adalah case ketiga, yaitu kombinasi beban 1.35 Jk dan 1.35 Jk tambah dengan 1.5 Qk. Mula-mula apa yang kita perlu buat adalah kira fix end moment menggunakan formula yang telah diberi, yaitu WL kosa 2 per 12, dan mendapat nilai 50.2 kNm dan 81.8 kNm. Kemudian menggunakan moment distribution method dengan menggunakan vektor 0.43 dan 0.57 hingga momen seimbang. Nilai akhir momen sendi yang kita dapat adalah sekitar 79.4 kNm. Seterusnya, kira shear force menggunakan keseimbangan momen dan dapat nilai seperti VAB 27.7 dan VBA 42.7. Seterusnya ini adalah yang terakhir, shear force diagram dan bending moment diagram. Mula-mula buat shear force diagram berdasarkan nilai daya Ricci yang telah kita kira sebelum ini. Garisan menunjukkan perubahan linear sepanjang span akibat beban seragam. Saya juga tentukan titik kosong sifar shear, yaitu pada jarak sekitar 1.2 hingga 1.3 meter. Ini penting untuk mencari momen maksimum. Seterusnya, kira pada mid span moment. Bagi setiap span menggunakan nilai shear tersebut untuk span 1 dan 2 dan 3 dan 4. Saya dapat momen sekitar 16.6 kNm hingga 33.1 kNm. Manakala bagi span tengah, yaitu span 2 dan 3, momen di sana lebih besar dengan nilai 70.4 kNm. Yang terakhir adalah lukis bending moment diagram. Kita boleh lihat momen negatif di sokongan, yaitu sekitar negatif 79.4, dan momen positif di tengah span. Ini menunjukkan tingkah laku rasuk yang dilakar di bawah beban seragam. Kedua-dua diagram ini menunjukkan dengan jelas taburan daya Ricci dan momen lentur sepanjang rasuk, serta membantu mengenal pasti lokasi momen maksimum untuk tujuan reka bentuk. Sekian, terima kasih.
I will start with the basic specification of the column. The column has a cross-section of 300 by 300 millimeters. The effective height is about 950 millimeters in the Z direction and 3000 millimeters in the Y direction after considering beam depth. The column is connected by a main beam and a secondary beam. The main beam is 200 and 500 by 50 millimeters, while the secondary beam is 200 by 500 millimeters. For material, we use concrete strength of 25 and steel strength is 500. Next, we calculate the moment of inertia using BH3/12. The column is equal inertia in both directions, while the beam have higher inertia, especially in the main beam. This indicates that the beams are stiffer than the column, which will influence the structural behavior. I will explain the stiffness and effective length. Stiffness is calculated using EI over L. The column stiffness is around 2.3 times 10 to the power of 5, whilst the beam have higher stiffness value. Using this, we determine the relative stiffness K. The value is about 0.12 in the Z direction and 0.1 in Y direction. These values are used to calculate the effective length of the column. The results show that the effective length is reduced compared to the actual height. The effective length is about 1785 millimeters in the z direction and 1770 millimeters in the y direction. Next, we calculate the radius of gradation, which is about 87 millimeters. From this, we determine the slenderness ratio, which is around 20 for both directions. Finally, I will present the slenderness check. We will calculate the limiting slenderness using parameter A, B, and C, along with the axial load ratio. The limiting value are about 41 for the z-axis and 34 for the y-axis. When we compare this with the calculated slenderness value, which are around 20, we can clearly see that the values are lower than the limits. This means the column does not behave as a slender column. Therefore, we conclude that the column is a non-slender column in both directions. Second other effect, the negligible that the column can be designed using the short column approach. Overall, the column is safe, stable, and meets the design requirement.